Hey guys, welcome back to another video. Today we're going to be solving Leetcode 162, find a peak element. In this problem, we're told that we're given we're told what a peak element is. A peak element is, we're told that it's an element that is strictly greater than its neighbors, and we're given an array called nums, and we want to find the peak element that is in this array of nums and return its index, okay? And we're told that if an array contains multiple peaks, we want to return the index to any of the potential peaks. So, and we may imagine that an element is always considered to be greater than a neighbor that is outside the array. So the numbers at the edges are always considered to be greater than the numbers outside. And we want to write an algorithm that runs in big O of log n time. And actually another kind of important constraint that we want to consider is this constraint over here, that adjacent elements, right, and elements next to each other cannot be equal to each other, right? They're not the same, and they'll always be different. So these are the kind of cases that we want to keep in mind. And so you might think, okay, this is super simple. We can just go through the entire list, right, in big O of n time, and it's super simple. We'll have 3 pointers, and then do comparisons, and whenever we find a peak, we'll return it. And that is possible. That would still be an efficient solution, but it's not the solution that we're told that we want to, the time complexity that the problem tells us that we have to return. We want to return an algorithm that runs in big O of log n time. What algorithm allows us to do that? Well, that's binary search. Binary search will allow us to write an algorithm that runs in that time. Okay, so let's actually get to coding. Before we get to coding it up, actually, sorry, let's kind of visualize what peaks are. So let's say we've got some dots right here. We've got some elements. That's an element. So we've got this peak. We've got these peaks, right? Let me try to connect them. Actually, some these are connected to each other. Oh, that was really bad. Okay, fab. So here we go. We have 2 peaks that we can we've got 2 peaks that we can see, right? These are the 2 peaks, right? So the elements on either side, on the left and right, are less than the peak elements. So we want to return either of these peaks, right? And again, it's super simple. We can just look at an element and say, okay, it's greater than its left, and it's greater than the right element, therefore it's a peak. But what's the case if we have these kind of elements, right? So these elements here are greater than the elements on the left-hand side, but there is no element on the right-hand side. And we can kind of visualize, we can kind of think of an example like 3, 2, 4. It looks like there's no peak here, right? Because we look at 2, which is the midpoint, and we'll say, okay, there is no actual peak, because this is not greater than either side. But remember, we can infer that these are zeros, or these are some number. If this was 0, this would be, I don't know, this would be infinity, negative infinity. So we can just assume that these elements on the edges are always greater than whatever element is over here. So in this case, we'll assume these are zeros. And we shall say 3 is greater than 0. That's true. 3 is also greater than 2. That's true. Therefore, this is a midpoint. In this case here, 4 is greater than 0. 4 is also greater than 2. Therefore, again, we have a midpoint. So that is the kind of output, right? Or not the output, but the kind of the intuition behind solving this. We're always guaranteed an answer, basically. So knowing this, how would we employ binary search? Well, let's take an example. I'll take this example over here and just copy paste that. So we have this example, right? And with binary search, we find a midway point. So we find this midpoint. Let's say the midpoint is initially going to be equal to 2. With binary search, remember, we always want to kind of discard a side. So we either want to discard the left-hand side, or we want to discard all the elements on the right-hand side based on some precondition. What is that condition going to actually be? Well, the example here, we have 2. Well, we say, is 2 greater than 1? No, it's not. Is it greater than, oh yeah, it is, sorry. Is it greater than 3? No, it's not. Therefore, this cannot be the midpoint. But which side do we want to look at? Well, let's take an example. We've got these points, and let's say we are at our midpoint, okay? Which side would we want to look at? Well, if we look down, if we look at the lesser element, well, that's not going to give us a peak, right? But if we look at the greater element, well, that is more likely to give us a peak. So this is kind of like a greedy approach, but we want to consider the element which is greater. So in this case, we can just discard the left-hand side, and we can say our next peak is going to, the midpoint is going to be equal to 3. And now we check, is 3 a peak? Well, 3 is greater than 2. We know that is true. And 3 is also greater than 1. Therefore, we find a peak at index 2, and we can therefore return 2. So I hope that makes sense. That's how we're going to employ binary search to solve this problem. Let's actually get to coding it up. So it's simple binary search boilerplate here, but I'm just going to write it up. So L and R is equal to 0 and length of nums, and actually length of nums minus 1, just to make our life a bit easier. And we're going to say while left is less than or equal to R, mid is going to be equal to left plus right divided by 2. This gives us our midpoint. And then we want to do the conditions, right? So we want to say if the number at midpoint is less than the number at mid minus 1, then we can say, well, we want to search everything on the left-hand side, or on the left-hand side, right? So we can say result equals mid minus 1. But there is an edge case. What if we were at position 0? If we were at position 0, we would get an out of bounds error. So what we want to do instead is say, as long as m is greater than 0 as well. Otherwise, I'm just going to copy this condition. This is going to be as long as m is less than the length of nums minus 1. Nums mid is less than this number over here. We'll set left pointer is equal to mid plus 1. Else, we'll simply just say if neither of these conditions are truthy, well, then we found our midpoint, haven't we? And then we can just return mid. So that's our solution. Because we're guaranteed an answer, we don't need to have any other return statement outside of this. So let's just submit our code. Let's check that it works. And it does not, because m is not defined. This should be mid, right? Mid and mid. Let's submit our code again. And now we see that we passed all 73 test cases with an optimal solution. So that's the code, guys. I hope this problem description made sense, and I hope the code also made sense. Fairly easy to write the code, but a bit tricky, especially when it comes to figuring out that solution of the condition for binary search. When do we actually want to discard which side? Coming up with the intuition behind that, it just is slightly tricky. So in terms of time complexity, well, we know it's going to be a big O over log n because it's binary search, and that's what we've returned. And also space complexity is just going to be auxiliary space only, so big O of 1. So with that being said, guys, I hope you enjoyed this video, and I'll catch you in the next one.